problem says basically that water is flowing as a steady stream from the faucet of a kitchen. So, and the problem says that we have the diameter of this part of the stream is of 1.96 centimeters, and that the flow can fill a container of 125 meters cubed in 16.3 seconds. And the problem is asking us for the diameter of the stream of water below the opening, below the opening of the faucet at 13 centimeters. So first we have to recall the Bernoulli's equation. We want to know the diameter, and the only relationship between the diameter and this equation is velocity. So we have to recall another equation. So by using this first equation, we can isolate the diameter from here, which we assume that is a circle because it's like a hole, and the water is passing through that hole. So it's pi times radius squared. That's the only relationship between the velocity and the diameter, and this part is also related to Bernoulli's equation. So first we'll solve this part. So in this part, it's quite easy to know the rate of flow. We know that the rate of flow is the volume over the time. So by dividing this, we'll get the rate of flow. But in order to have it in the good units, we have to convert it. We have to convert from sorry, this was in centimeters. We have to convert it from centimeters to meters. 1 meters cubed over 1 million centimeters. 7.6668 times 8 minus 6 meters cubed over seconds. So now that we know the rate of flow, it's time to know these values. We know that the area 1 times the velocity 1 equals the area 2 times the velocity 2. But so we only have to isolate one velocity. Why? Because from the area we only know one radius. So it's better to use the one we know the radius. So you only have to replace, and also you have to convert this into meters. So you will get 0.096 meters, and the radius is equal 0.48 meters. So you only have to isolate B.
So then B is the rate of flow over time. I only have to substitute the values.
.059 times 10 to the minus 3 meters per second. Now we have the first velocity. So now that we already have this part and the velocity, that was 1.4, was this one, and we still want to know the radius and this velocity. It's easier for we have to use a second equation, which is Bernoulli's equation, in order to first get the second velocity and then the radius. So from Bernoulli's equation we know all these values except for the second velocity. In this case, since the water is touching air all the time, we can assume that these ones are equals 1 atmosphere. We know our first y, we'll place it here from the bottom, and this is our final y. So since this is the lowest point, we can assume that this part equals 0. You can notice that since we have in both sides of the equation in every term the density, we can cancel out that too. So we only get this part and we only have to isolate B.
And we got 1.597 meters per second. Now we only have to substitute the value in this equation in order to have the radius and then to get the diameter. Now we only have to isolate r from this equation in order to then have the diameter. So now that you get the value from the radius, you have to multiply it by 2 in order to get the diameter, and then you get 2.47 meter times 10 to the minus 3 meters, and then you have to transform that into centimeters, so you'll get 0.247 centimeters of the diameter, and that's its final answer.